All right. Happy Friday. We are going to be talking about digital circuits today. But before that, a few announcements as usual. So today is Feb 5th. We are going over class 4 material. So the corresponding quiz is daily quiz number 4, which is active on Gradescope. So I would recommend you guys to complete that quiz sometime today. The homework that is due, that's coming up, homework 2 is due Tuesday, Feb 9th on Gradescope. A few of you have already done that in, so that's good news. And I will be posting homework 3 on Tuesday as well. Now, in terms of studio, it looks like several of you have already completed Studio 1, both the TA checkoff as well as the studio report submission on Gradescope. So that's due Feb 17th. So you still have some more time to complete that. But I want to emphasize that every student needs to do this, and both things are required, right? So without a checkoff, your Gradescope submission would be considered invalid. So make sure that you complete both those things. Let's see. Your next studio is Studio 2, in which I'm going to encourage you guys to start pairing up in groups of 2. And I will post that over the weekend, so you can take a look at that starting on Saturday, and maybe if you need some help on Sunday, we have help sessions scheduled for Sunday as well, so you can get started early. You will have a week after Feb 17th. That's when Studio 2 will be due. Questions or concerns right now? One, five. Just a note there, that I forgot to mention. When you team up, I encourage you to team up with a student from the same section so that there is no confusion about the availability and who is, so to avoid all those problems in terms of managing time, um, I recommend you to pick a partner from your section. Okay, let's move on. So we are talking about digital circuits here, and the goal is to be able to look at logic gates down to the transistor level, right? So how do you implement logic functions using CMOS transistors? That's the goal of today's lecture. And the logic functions that we will look at can be as simple as a buffer or a NOT gate. We will try to take a look at NAND, NOR, and OR. So these are the logic gates that we are going to look at and say, all right, how do you actually synthesize this logic functionality using transistors? So we are going to all the lowest level possible in that aspect. Now, using some of these gates, you could also derive exclusive OR and exclusive NOR logic functions. Right? So these are not direct logic functions like those, but those are derived from the logic functions that are described in red, listed in red. And we are doing this using CMOS technology, which is going to be based off of MOSFET transistors. And just before I begin talking about this, I want to mention basic gates. In terms of basic gates, we have NOT, and an OR. Those three are considered basic gates. not and OR. The other gates are not in the category of basic gates. For example, NAND and NOR are considered to be universal gates because you could synthesize any logic functions using just NAND gates or just NOR gates. But in terms of basic gates, the idea is you can synthesize any function, any logic function that you come across using some combination of these three gates. We'll begin talking about basic Boolean operations first, because we are talking about logic functions. So let's take it what those three basic operations are. Like I said, and, or, and not. So let's define a Boolean variable first. So we have learned what variable means in our math classes, but a Boolean variable is simply a variable that can take one of two values, 0 or 1. And then you can have a Boolean variable that is an input. You can have a Boolean variable that is an output. So you can have input binary variable, input or output binary variable. But no matter if it is input or output, and sometimes you might want to monitor intermediate binary variables. No matter what it is, it can take only one of two values, 0 or 1. But there are some special cases, when we go on ahead with our lectures, we will see that there is also one more state that is possible, which is the high impedance state. We'll talk more about that later. Now, when you have a bunch of Boolean variables, you can combine them using these operations and call that resulting function as a logic expression. Now, if a logic expression is false, it has a value of 0. And if a logic expression is true, it has a value of 1. These are logic 0 and logic 1. But if you just think about logic 0 or logic 1, if you try to associate that with something real, right, you can say, all right, hot and cold, light is on, light is off, high and low. So every real quantity that could be separated into two states or binary states, you could associate that real quantity in terms of a binary variable. And you can say, all right, when this is cold, it is a logic 0. And I'm going to express hot with a logic 1. But clearly, nothing is absolutely cold or hot, right? It's all relative. So you have to, inevitably, you have to talk about or define a set of temperatures that you are going to quantify as low, cold, and then some other set of temperatures that you would quantify as hot, and then associate that with the 1. What I'm trying to say is, when we think of binary 0 and 1, they are not just one value, they are actually a range of voltages in a circuit. Talk more about that later. Now, basic Boolean operations, like I said, and or not, the following three tables over here are listing the three truth tables of those three Boolean operations. So for example, all the way to the left, we have X as an input binary variable, Y another input binary variable, and then we have X and Y. We can associate another binary output variable for this. We can say Z is X and Y, which you could write as X, and then that dot indicates the AND operation, and then Y is not the same as convolution. What do you mean? Which particular thing is not the same as the convolution? No. So not is simply like flipping the bit, right? So for example, if we think back to our previous lectures, we said hey, in order to find the 2's complement of some bit sequence, then you would have to flip all the bits and add 1 to it, right? That flipping operation, or turning a 0 into a 1 or 1 into a 0, isn't convolution only for analog things anyway? No. So there is continuous convolution. There is also a discrete convolution. So you could have convolution for both continuous things and discrete things. It's not just for one thing, but you use convolution to say find an output, find the output of a linear time invariant system when you are given the impulse response and the input of for that system, right? So it's meant for a different purpose. Right. So here, let me, since you guys raised the topic of convolution, you will see more of this in signals and systems, but let's just take a detour here. So suppose you have some system, right? This is a black box. I don't know. It could be a circuit. It could be a room. It could be anything that you're trying to analyze. The first requirement for convolution to work is that it has to be linear and it has to be time invariant. We call those systems linear time invariant, LTI systems. So convolution is used to actually compute mathematically what would be the output of this system when you are given two things. One, the input x of t, and you would also have to describe or characterize the LTI system using its impulse response. We call that h of t, right? So if you are given if you know the input and if you know something about the system, not something, everything about the system because you have characterized it, then you can convolve these two things, x and h, to find y. We write that as x of t convolved with h of t. And this is for continuous systems, but you can extend this to y of n equals x of n convolved with h of n. So that is discrete convolution that is applicable for discrete time LTI systems. You will see more of this in 2410, signals and systems. All right, let's come back. So we are talking about and truth table, right? So let me write down what these are. These are truth tables. And the one good thing about truth tables is that it uniquely describes a logic function. So for and between two input variables x and y, this is it. This is the only truth table that you could have. It is unique representation of a logic function. There are many ways to express a logic function. You will see that you can write statements, you can write logic expressions, you can express them in many ways, but truth table is one way of doing it in a unique manner. All right, so that's x and y. The and operator can be written in a compact fashion by just putting a dot in the middle of the two input variables. Now, the way you look at z, which is and operation, z equals x and y, is both the input variables have to be true in order for the output to be true, right? So if x is true and y is true, then the logic expression z equals x and y is going to be true, right? Both have to be true, this and this, right? That's the reason we are using that word and to describe the logic function. Mac and cheese, right? So both have to be there in order for it to be a healthy meal. Oh no, this is like comp sci all over again. It is going to soon become very, very electrical. Hold on to your seats. So bottom line is both have to be true in order for the output to be true, right? So that's kind of like the defining case for the and logic function. Next, x, y. Again, two input binary variables. The output is X or Y. And now we can also have, say, I don't know, A equals X or Y. And as you can see, we are using the plus sign to indicate the OR operation. This or this, right? One or the other. If it is true, then the output is true, right? So you see, it is true here, it is true here, and over here, both of them are true. So those are the three cases in which at least one input binary variable is true, leading to the output becoming a 1 for those three cases. That's your OR logic operation. Quick question. Can I have more than two inputs for AND? Can I have more than two inputs for OR? Absolutely yes. So you can have a 3-input AND gate. You can have a 4-input AND gate. But the problem is, as you are increasing the number of inputs to this gate, there are some fan-in limitations you will run into. Meaning, we talked about the fact that 0 is actually not 0 and 1 is not actually a 1. It's actually representative of a range of voltages, right? So when you are trying to put in more and more inputs into a logic gate, you are kind of risking the voltages to be not representative of 0 or 1 the way you would want them to, right? So that's called fan in limit. And every logic gate will have a fan in limit. In fact, it'll have a fan out limit as well. More about that as we progress through this digital circuits lecture. Now, the last logic gate that we have here is the NOT gate, right? X equals not X. And the way you express this is simply saying, let's say I have A here, B. So let's say B. B equals X complement, right? So not X or a bar over X, that's what indicates a flipping operation or complement operation, an inversion operation, a NOT operation. Like all of these things are interchangeable. And there are other ways of doing that as well. Sometimes you will see in textbooks an apostrophe on top of X, which is also the same thing as saying X complement. And it's very simple, right? 0 becomes a 1 at the output, and if 1 goes into the NOT gate, you get a 0, right? 3 truth tables for 3 basic logic functions. Next, we'll try to look at, apart from the truth tables that you see on the left column, we also have in the middle the Boolean equations or logic expressions or logic equations. Again, these three things are kind of, the same thing. Z, which is the output, equals X complement. Next, Z equals X and Y, or, if you're trying to write it in a very compact manner, provided there is no confusion, then you can write it this way, just XY. No need to write the dot in the middle. And then we talked about the plus sign, right? So this is not an arithmetic addition. This is a logical OR, right? So for example, let me just write that note down. Not arithmetic sum. This is logical OR, right? So when you say 1 plus 1, you say 2, that's okay for arithmetic sum. But in our case, we are not going to say 1 plus 1. We are going to say 1 or 1, which is not 2, which is 1, right? So that's you. So you need to start looking at how your arithmetic algebra and your arithmetic operations are going to be different from Boolean algebra and Boolean expressions. Some might be the same, right? So, for example, if I take a Boolean variable, say B, it's a binary variable, right? So it could be a 0, could be a 1. And if I multiply that with a 0, what do I get? Well, if it's a AND operation, you get a 0. And if it were to be a arithmetic operation, it would also be a 0, right? So sometimes arithmetic algebra and Boolean algebra tend to be, luckily, they are going to result in the same thing. But for all generic purposes, you should assume that they don't. Because arithmetic algebra, things could take a value between anywhere 0 to 9. Now we are in the binary world, so we are going to limit the Boolean variables to be either be 0 or a 1. All right, so I hope that helps. Let's take a look at some of the symbols here, because symbols are very helpful in order to, again, express a logic function, right? So remember, just a few minutes ago, I said there are many different ways of expressing a logic function. The most unique way of doing it is to use a truth table. But other ways of doing it, which actually are not unique, are Boolean expressions or binary expressions or logic expressions, and symbols drawn up one after the other, connected using wires. That's a logic diagram, right? So logic diagram can also express a logic function, but it doesn't do that uniquely, right? You could have many different ways of drawing a logic function. So we'll take a look at all these ideas that are coming up later. Now, I want to talk a little bit more about maybe this. So what I'll do is I will simply take a picture of this guy and paste it on a next page, because I want to go through some discussion about this, right? So this is the truth table for the OR gate. By the way, I don't think I spent too much time on the symbols. All right, let's come back to this. The inverter is a triangle followed by a bubble. The bubble is actually what signifies inversion. The triangle is representative of a buffer operation, right? The triangle is just the buffer, also called as the identity function. Whatever goes in comes out. So that's a buffer or identity, right? So if X goes in, X comes out, right? There's no change there. But if you put a bubble at the output of that triangle, that indicates that things are actually getting flipped. They are getting complemented. They are getting inverted. They are getting, what else was it? Not. That's the not operation, right? So that's your symbol, triangle followed by a bubble. For AND, it is sort of a D. X and Y are your inputs going in. Z is your binary output variable. Now, because you have two inputs here, again, you can have 0, 0 or 0, 1 or 1, 0 or 1, 1, right? 4 possible combinations for the two inputs, given that X and Y are binary. And for each of those 4 combinations, you will get a particular 0 or a 1 for the output Z. And because this is AND, Z is only going to be 1 when X and Y are both 1. So big D is your symbol. And the way you write Z is, say, X and Y, or simply XY. And like I said, you can also have a 3 input X, Y, Z, and then you can call this F, X, Y, Z. A 3 input AND gate. Next, for OR, there is a arc and a triangle. So this is X or Y, and again, you can have more than 2 inputs. You can have 3 input OR gate. You can have 4 input OR gate. However, we need to still be aware that we could run into fan-in limit. Now, coming to this. One way to write an expression for Z, so let's say this is Z. We define this guy as, say, Z. So Z is X or Y, right? This is one way of writing the logic expression. However, I said that logic expressions are not unique. So let's try to look at an alternative logic expression for this OR function by observing the truth table a little bit more. So for this, I will ask you guys a question. When is Z1? When is Z equals 1? Right. You're right. So let's try to build an understanding of where that comes from. So Andrew wrote the answer already, but let's try to get to that in a sort of a step-by-step process. So when is Z 1? Well, you could say Z is 1 at 3 different places, right? The first place is this guy, the second place is this guy, the second one, and the third one. So there are 3 places where Z is 1, and the first place is Z is 1 when X equals 0 and Y equals 1. That's the first time it happens. Alternatively, you can say copy, paste. Z equals 1 when X complement equals 1 and Y equals 1. Right. This is the same thing as this, right? X equals 0 means X complement equals 1. Now, notice what you're trying to do here. You're observing the ones, right? And you're trying to use the AND operation, meaning you're trying to convert things into that unique entry in the AND function, which is X is 1, Y is 1, output Z is 1, right? So you're trying to turn things to 1 so that when you AND them, your output is 1, right? So you're manipulating the variables in order for that to happen. So when Z is 1 is all of this, right? So that gives me the first condition, which is what? X complement and Y. And similarly, for this guy, you can do the same thing, right? What would you say for this guy? Well, you would say X has to be a 1 and Y has to be a 0. And then similarly, you can say 1 for this guy. You can say X has to be a 1 and Y has to be a 1. Now, Z is 1 when this happens or this happens or this happens. Meaning, the expression for Z is X complement and Y or X and Y complement or X and Y. You guys see that? And it turns out that this particular logic expression is not in its simplest form. When you simplify it, you will end up with this guy. So, that's to be noted that things can be simplified, and there are sort of boring ways to do this. I should say boring and not so systematic, not so structured way of simplifying expressions. But as we go through our lectures, we will see that they are very systematic and easy ways of getting the simplest logic expressions. So I hope that discussion helped you guys look at a truth table and be able to talk about a logic expression for that. Okay, let's move on here. Now, when it comes to a logic signal, the digital logic ignores the analog by quantizing a real value. do we not do Boolean algebra? We are going to do Boolean algebra. So after digital circuits, we get into Boolean algebra. So that's lecture 3. All right. So digital logic ignores analog by quantizing a real value. All right. So lots of new words there. What is a quantizer? What do you mean by ignoring the analog? Let's take a look at this by looking at the analog to digital conversion process. So suppose you have, say, an analog signal, right? So what I'm going to do is I'm going to take a voltage waveform, for example, and I'm going to define the x-axis over here as time, and the y-axis could be a voltage, could be a current. Just for the sake of discussion, I will say this is a voltage, right? And let us say that this voltage waveform as a function of time is an analog waveform. So it's a continuous one, right? So I'm going to sketch up some arbitrary continuous waveform here. It doesn't really matter, but I've just sketched some, you know, sinusoidal looking like waveform here. Now, this is analog. Now, the first question is, if I had to feed this into a computer, so suppose I wanted to input this voltage waveform, the data of this voltage waveform into a computer, how does it happen? Am I going to ask my computer to store and process this value and this value and this, each and every value in time? Or am I going to convert this analog waveform to a digital waveform and then convert things into a bunch of zeros and ones and then let the computer process them or store them, right? So we are going to try to convert this continuous waveform into a bunch of samples first, right? Something that is discrete in terms of time. So for that, I need a sampler, right? So something that can pick certain values of the signal as opposed to all the value of the signal. So let's say I'm going to highlight this thing with in terms of like a blue mark. So let's say I pick the first value, this value, just arbitrarily sketching this, hopefully uniformly. So that process is sampling, right? So I have sampled the signal at different times. Starting from here, I got that value, I got that value, I got that value, then that, that, and so on, right? Now, when I did this sampling, I was worried about something. I was worried about the fact that if I don't sample the signal fast enough, then I may lose data, right? I may lose the information of that voltage waveform. But the way I have sketched it, I actually have a lot of samples. Actually, I have 1, 2, 3, 4, 5, 6, 7, 8, 8 samples in one period. I actually need just 2 samples in a period. Absolutely. Andrew has put it down. 2 times the highest frequency. Yes. So that is the least sampling rate that will guarantee that I will be able to reconstruct the signal. But I have done oversampling. All right. I have done 8 times, 8 samples in one time period. So I'm good here. I will be able to reconstruct. And you can clearly see if I just gave you the black dots, and even if you had to take a very simple reconstruction, you could just connect them by like straight lines and you would say, oh yeah, it looks like the signal. It's not like I'm losing any information. All right, so that is the sampling process. Now what the result of the sampling process is are discrete values that describe the amplitude of the voltage waveform at T1, T2, T3, T4, and so on. So let us just say, all right, so this is say, I don't know, 1 point, oh, too big, 1.1, 2.3, say this is 3.1, 2.2, negative 0.5, and so on, right? So you've got discrete values in amplitude at sampling times. But still, these are a bunch of ones and twos and threes. Of course, these are in decimal. Now, how do you go from this to a bunch of zeros and ones that a computer can process? Well, of course, you need to first come up with how many bits are you going to need. I actually need to say, how many bits do you have? So for the sake of discussion, let us say we have a 3-bit quantizer. So 3 bits actually tells me that it is going to have 8 levels, right? So 8 levels, that means that the highest amplitude in my signal all the way down to the lowest amplitude in my signal, that is called the dynamic range of the signal. That dynamic range can be split up into a maximum of 8 levels. So let me use a different color to describe the granularity in the vertical direction. So let's say I say, right, this is right there, and then 1, 2, 3, 4, 5, 6, 7, and 8. Right. So all those pink lines are essentially indicating the 8 levels for which I have a unique 3-bit sequence. So for example, this could be 000, this could be 001, this could be 010, 011. Doesn't really matter what these are, they just have to be consistent, right? So now I'm ready to actually talk about the signal without worrying about its analog nature or the discrete samples. I'm essentially going to say, all right, 0, 1, 0. This is what is the closest level. 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, and so on, right? So now I have a bit sequence, right? So this process that we talked about is essentially the function of an analog to digital converter. But as you can see, the number of bits that you have in the quantizer determines how fine is your granularity in the y direction. But for the horizontal direction, sampling rate would be the determining factor. And like Andrew mentioned, the Nyquist rate of a signal is the limit. 2 times the highest frequency is the limiting frequency at which you need to sample the signal in order to be able to reconstruct it from its samples. All right. So that's what this means. We are ignoring the quantization of the real value. All we are doing is we are looking at these bunch of zeros and ones and then constructing circuits that can manipulate those zeros and ones. Now, coming back to the concept of a range of voltages as opposed to a 0 and 1, right? So when we said a binary or logic 0 and logic 1, logic 0 is indicative of lower voltages, maybe 0 to 1.5, right? So 0 volts to 1.5 volts, I'm going to use that as the voltage range for logic 0. And then for logic 1, I'm going to say, all right, every voltage that is between, say, 3.5 and 5 is logic 1 or high. And then, of course, because I have isolated 2 regions, there is also a no man's land that is created between those two. So, for example, in our case, 1.5 to 3.5 is the undefined region. So it's the gray zone or the undefined region. The signal is neither a 0 nor a 1 over there. And we don't want to spend time over there because the person who is trying to do some interesting logic functions is not going to know whether the bit is a 0 or a 1. All right, let's move on here. And this brings us into the logic levels for, say, CMOS, right? So logic 1 or high level is any voltage between 3.5 and 5. And logic low or logic 0 is anything between 0 and 1.5. And like I said, in the middle, you have this gray zone where it is undefined. So if you are trying to look at the value of the voltage to be able to find out whether it's a 0 or a 1, you don't want to be in that gray zone, right? You want to be, where do you want to be? Let's take a look at this and talk about where would you ideally want to be. So the high low just reads 1 bit. This is to talk about 1 bit, right? But this is depending on how many bits you have, it is going to be the same voltage level for every bit. So we are just talking about one bit here. So do you want to be, so let me pose the question to you guys this way. Do you want to be over here, or do you want to be over there? Higher, blue. All right. So why do you want to be at the blue region? Make sure of the value. Yeah. So this is, what I call a strong one, right? Less issues due to parasitic things. All right, less issues. I like that, right? It is going to take a lot of noise to move this guy over here, but it is going to take a very small amount of noise to move this guy over here, right? So it's very, if you are here, you are more tolerant to noise, but if you are here, you are less tolerant to noise. So I'm going to call this a strong one, right? 4.9, 4.8. These are good because it's going to take a lot of noise to corrupt that one. But this is what I call a weak one, right? Very easily you can, get it confused with the undefined region. And the same thing applies here, right? So let me just copy this guy and then paste it over here, because there's going to be a strong 0 and a strong 1. Will this work? Nope. I need to go opposite. You got it, right? So if I'm close to the 1.4, 1.45, I'm getting worried, right? Because any small amount of noise in my circuit, whether it be thermal noise or some error, some noise, it could push it into the middle. So what if you are in the middle? Well, if you are in the middle, you are in the undefined region, right? So right away you don't know what that is. So it's undefined. If you want to carry out logic functions that result in logic operations that the user intends, then you need to be here or you need to be here. Yeah, right. So it's like undefined. So it could be a 0, could be a 1, but no matter what it is unreliable. And worse, it could keep changing. All right. So this kind of, leads us, and we are not going to do it right now, but this discussion leads us into noise margin, right? Noise margin is what is the amount of noise a logic level can tolerate. So we are going to talk about that when we discuss noise margin. That's coming up later, but that it has to do with the weak 1 and the strong 1 and the weak 0 and the strong 0. Some voltages are going to be more prone to noise than others, less tolerant to noise than others. Let's see. Now let's talk about the question that we actually, that's kind of the core of the discussion today. How are Boolean operations implemented? Now, if you want to implement not, if you want to implement and, or, NAND, NOR, how do you implement that? We have to have undefined logic level for all cases. Yes. So no matter what you're looking at, you will have that undefined region. The goal is not to be there, right? So when you have hot and cold, you are going to say some temperatures are cold and some temperatures are hot, right? You and in the middle, you would want some zone of temperatures that don't qualify as either hot or cold, because if you did, then the distinguishing factor between those temperatures, those levels, is going to disappear, right? So the whole point of having like things in binary is lost if you didn't have that undefined region. Transistors, brilliant. Yes, transistors. Well, a specific type of transistors, right? We are not looking at bipolar junction transistors here. We are looking at MOSFETs here. Yes. Let's see, transistors, yes. Let's take a look. Let's see. I actually want to also discuss something interesting. All right, let's see. After, sure, let's do this. Let's try to talk about identity function. Identity function. And then not function. So these are two logic functions that are pretty basic. Now what I'm going to do is I'm going to use a circuit model to describe identity and to describe not. So what I'll do is I will use a constant voltage source, say some Vs. This is a constant voltage source. It's always there. And then I'm going to connect this constant voltage source to a light bulb. And in the middle, to control the current through the light bulb, I'm going to put a switch in the middle there. And of course, the switch can either be open or be closed, right? There are two states for a switch. Either it is open or it is closed. So let's say when it is open, switch open. And the state of the switch, let us say X is denoting the state of the switch and Y is denoting the state of the light bulb, right? So let's say X, switch open means X equals 0. And when switch is open, what do you have for the light? Zero, right? Y equals 0. Now, when you make X equals 1, right? What happens to Y? 1. You see that? So I'm assuming that the power supply is enough to turn on the light bulb here. But when X is 0, Y is 0, X is 1, Y is 1, right? What is that? X, the input is the same as the output. That's your identity function, right? So that the way we describe that is this: X, Y. Whatever goes in comes out, right? So the output binary variable, I use the light bulb to model the output of this buffer, or to model the output of the identity function. And then I use the state of the switch as the input. Now here is an interesting question. What would you need to do to this circuit diagram to come up with the circuit model of a not function? Can you guys, what should I change in this circuit diagram? Switch open equals 1. Oh, well, I don't want to define things in a different way. No, put the light in parallel. Good job, brilliant. All right, so if I play around with the position of the switch, I get it done. Look at this. And just for simplicity, I'm going to put a small resistor there so that I don't end up into some ambiguous situations. Now I'm going to put the switch in parallel with my light bulb here. But I'm going to use the same definition, right? I'm going to use the same mapping, which means when switch is open, X is 0, when light is off, Y is 0. The mapping is the same. I still have Vs. I have some small resistance here. Then I have the X here, then the Y here, right? Now what is going to happen? When X is 0, switch is open, what is Y? 1, right? Because it's lighting up now, right? Because no current goes through the switch, all the current has to go through the light, turning it on. But when X is 1, Y is going to be what? 0, right? Because you have a switch over here, small resistance, need to work hard to turn on the light. All the current, at least almost all the current, is going to flow through the switch, which means the light is going to be off. You guys see that? This is your inverter, right? Whatever goes in has been flipped. So you can do some interesting, you know, you can express these logic functions using circuit models. Actually, if you're interested, if you play Minecraft, you can use Redstone to make circuits over there for identity, for NOT, for AND, and all that. So there are lots of interesting angles using which you can look at logic functions. Now, let's extend this conversation a little bit. How about AND? Where do you think I need to? Yeah. Can you do my? All right, I'm gonna try. So actually, my son taught me all those things. I didn't know. Second YouTube channel. I'm gonna try, you guys. It's very interesting. Yeah. Um, of course. All right. So an AND function. Somebody already said the answer there. Two switches in series with light. Good. So if I put two switches in series with the light bulb, I get my AND function, right? So still this is my voltage source. I have one switch here, other switch there, then I have the light bulb there. And my light bulb is my output Y, and my state of the switch is X1, and state of the second switch is X2, and this gives me, right, both switches have to be on in order for light bulb to be on. I'm still using the same mapping, right? Still same mapping. Switch open means X0, switch closed means X1, light off means X0, Y0, light on means Y1. So it's the same mapping. So that is your model of AND. How about NAND? NAND is opposite of AND. In other words, it is the complement of the AND function. So it's like this. Y equals, it should be this. X1, X2, AND function, and then complement it. Put two switches in series, the switch system parallel to right. Beautiful. That's exactly right. The same game as this, right? Switch in series, turn it into parallel, you flip it. Switches in series here, put them in parallel with the light, and you're done. So you have Vs, you have resistor, and then you have the two switches that are in parallel with the light bulb. This is your Vs, Rs, X1, X2, light bulb Y. Done. Both switches in series, but parallel to the light. Got it. Now, what would be one statement you could say about AND or NAND. One statement you probably could say easily is that the inputs should be in series. Can I say that? Whether it be 2 inputs or 3 inputs, no matter how many inputs I have to the AND or the NAND, they need to be in series, right? Switches need to be in series for AND or NAND operations to work. You guys agree with that? Beautiful. For OR and NOR, switches need to be parallel. You got it. All right, you guys are going ahead way fast. All right, I'm going to quickly do OR and NOR over here. And as you guessed, they need to be in parallel. So for this guy, I'm going to need VS over here. Then I'm going to need a parallel switch there. Oh, sorry. Going to need switch, switch, light bulb. X1, X2, Y, VS, right? That gives me R. Current can go through this path or it can go through this path. Next, switch system in series with the light. Switch system XNOR would be 2 switches in parallel to the light. No, actually, for exclusive OR and exclusive NOR, you have to build those functions using basic gates. So you can either use NAND or NOR gates to do that, or you need to do like and or not and or and not combinations. So it's not very straightforward, is what I'm trying to say. For NOR, what do I need? NOR is exactly the opposite of OR, right? So this should be X1 or X2 complemented. That's what is NOR. And we have seen you get all in parallel. Beautiful. So I still need my VS, some resistance there, and I'm going to turn that parallel combination in parallel with the light. You see that? That will give me a NOR operation. More about these things later, but I hope that this gives you an understanding of how do you arrange the switches, in what configuration should I arrange them in order to get uh, uh, if I do it in series, I get AND and NAND. If I do it in parallel, then I may get OR and NOR. And if I just flip the position from series to parallel, I will be inverting the variable. Right? So the circuit model uh, helps you kind of solidify, So these ideas, what I'm hoping for is circuit models are easy. Because you have seen them maybe previously in intro to ECSE or somewhere. When you get to circuits with transistors in them, you can still borrow the configurations, right? Switches need to be in series, switches need to be in parallel to get that function. So that's what I'm hoping for, that connection to be established. Now, for a switch, in this case an electronic switch, we are going to use the fastest switch that is available. What is that? 3-terminal device that can switch on and off electronically, right? That is your transistor. And the type of transistor that we are going to be focusing on is the metal oxide semiconductor field effect transistor. So the MOSFET. It's a 3-terminal device. Now I realize that some of you may not have seen transistors, and we are not actually going to be going in too deep in terms of the transistors here. My goal is to be able to show you how it can work as a switch. Transistors can also work as amplifiers. We are not going to be dealing with that for digital circuits. What we worry about in digital is how can I use this transistor in this on-off state, in the switching state as a switching application. That's what I'm going to be worried about. So what are the three terminals for a transistor? Well, it depends on the transistor, right? So if it was a BJT, the bipolar junction transistor, then the three terminals would have been emitter, base, and collector. Something that emits electrons, something that is able to control whether electrons are able to make it to the collector or not, and then the collector is sort of where all the charge is collected, right? Three terminals. The base is what controls the state of that BJT switch, BJT transistor acting as a switch. That's the story for BJT. For our MOS transistors, we have three terminals again. What are those? We have a gate, we have a source, and we have a drain. And I hope you see the similarity in terms of naming convention. Gate is sort of the base. Source is like the emitter in the BJT. Drain is sort of the collector in BJT. Source to drain, depending on the gate. Gate is open, then you may or may not be, right? So let's talk about what gate open means and gate close means in a little bit. So the switch, you know, when you draw a switch, you simply draw this diagram of a switch where there are two positions, right? Open and close. Now, I'm not going to actually flip a switch manually, mechanically, in order for that transistor to, switch on and off. I'm going to do this electronically, which means I need some electrical quantity to control the state of the switch. And I have a voltage. So if I have a voltage, and this is the voltage at the gate with respect to the source terminal, if I increase that voltage such that it is greater than some threshold voltage Vt, then the switch will close. And when the switch closes, you can see that the source terminal over here will get connected to the drain terminal there, which means some current can flow through the transistor. And R on essentially is indicating the on state resistance of that transistor. But if I do not go over that threshold voltage, then I may not be able to switch the transistor on, which means it is off, which means the source and the drain are not connected. That switch is open. Now the symbol of the MOS transistor is this. This is your gate. This is what you control. This is the only thing that you control, gate voltage. There are two other terminals, source and drain. So by manipulating or controlling this gate voltage with respect to the source terminal, because I need the other terminal to be with respect to, right, like as a reference. So gate voltage, if it is with respect to the source, if it is greater than a threshold, then these two guys are connected, or if it is not enough, then these two guys will be disconnected. Or the words, there will be a pretty high resistance between the 2 points, which means that it is not going to allow current to flow through those two terminals. So let us draw these states in simple diagrams. So when you have VGS, voltage that you apply at the gate terminal with respect to the source, if it is greater than or equal to some threshold voltage Vt, then the source terminal over here will be connected. I'm ignoring the on resistance here, but it will be connected to the drain terminal. However, if VGS, the voltage at the gate terminal, is less than Vt, if it is low, then the source and the drain are disconnected, there is an open circuit or a very, very large resistance, which means that it is going to not offer the current to flow through it. So control gate voltage to either connect these 2 points or disconnect the 2 points. That is your two extremes of transistor operation as a switch. Only worried about whether you connect them or you don't connect them. Now, there are two variations of this. The one that we have been talking about is the traditional, like the nMOS transistor, but there is also the opposite of it, the pMOS transistor. I also want to talk about these three words: the source, the drain, and the gate. Those three terminals in some context that is very commonly used, right? So suppose you have a room, right? You have a room here. All of this is a room, and there is a door in the middle, and you are standing at the door or the gate, and then there are some people outside the room, right? So the only way people can enter the room is if you open the door, right? So when you open the door, and the only control you have is here. The door is what you control. You don't control people. You don't control room. So people can enter when door is open. And of course, the alternate is people will not be able to enter, cannot enter when door is closed. Now, the way you can tie this to the three terminals, source, drain, and gate, is room is sort of where things are ending up, right? So that's like the drain or the collector for BJT. Door is kind of like the gate, allows people to go in or does not allow them to go in. And then people are the source. So the question is, depending on the gate terminal voltage with respect to the source, either charge can go in or current can flow through or cannot. Right? That's how you can think of it. Let's see. I also want to talk about what are some things that make an nMOS transistor. nMOS stands for N-channel metal oxide semiconductor field effector transistor, MOS transistor. So what you have in this case is kind of a big substrate. I just do this. And then you have two negatively doped materials over here. But this guy is all positive. So a lot of more positive charge in the substrate. So this guy is the substrate or the body of the transistor. This is your drain. This is your source. And then in the middle, you have a metal. That's your gate. And then there is some oxide layer in the middle, which that's there underneath that metal, which is why it's called the metal oxide. Now, if you need conduction, right, between source and drain, you would have to give the gate voltage to be something that is positive, right? So for example, if you connect this to a voltage source such that all the positive charge is accumulated on that side of the metal, then what happens is all the negative charge will form in that particular layer, which is identified as the N channel. That's the N channel, which allows connection between the source and the drain terminal through that N. Now, if you did not have a positive charge accumulate over there, for example, if you make the gate voltage with respect to source to be a ground, then you would have no negative charge would accumulate in that channel, which means that you would have the source and the drain to be disconnected. And this story is actually kind of flipped for the pMOS transistor. So this will be negatively doped, these two guys will be positive, and you are looking for positive charges to provide that particular channel. And of course, for that to happen, you would need to connect this with a negative value. So everything kind of like complements for the pMOS transistor or the P-channel MOSFET. But that's what it is, a substrate that is positively doped semiconductor. On top of that, you are adding two negatively doped regions. So more negative charge there, more negative charge there. Then you are attaching a metal in the middle, and that's what you're calling your gate terminal. And when you connect it to a voltage supply and give it, say, some plus 5 volts or something, all that negative charge accumulating over there forms a N channel, allowing the current to flow. And for nMOS, you actually connect the substrate to ground as well as the source to ground. Source and substrate are actually connected to the same potential. So this way, the direction of conventional current will be from drain, whatever you have connected to drain, through that to there. Now, in terms of symbol for nMOS or the N-channel MOSFET, we are going to use this. And it's kind of clear, right? This is our gate, this is our drain, this is our source, and this is kind of our channel. That's where we want to, that's the N channel that we want to establish for current to flow through, or that source and drain terminals to be connected. But on the left here, we also show the substrate. That's your substrate, and which is connected to ground here. We are not going to be needing to sketch the substrate every time. We will just use the simple 3-terminal nMOS transistor, and we often don't draw it horizontally like this. We actually draw it like this. So I've got the source, gate here, a drain over there, and source over there. Now, we said in order for that N channel to be established and that connection to be formed, you need a high potential at the gate, right? But if there isn't, when gate voltage with respect to source is 0, then the switch is off. Only when the gate voltage is high enough, then the switch is on, when that N channel is established. And for this, you can say, all right, logic 0, 0 volts. Logic 1, very high, VDD, right? Typically, it can be between 1 and 5 volts, but we are going to be referring to VDD as 5 volts, a high voltage. So let's take a look at this table here and try to draw some even simpler diagrams. What does this 0 indicate? Well, that simply indicates that the voltage at the gate with respect to the source is less than some threshold voltage VT. Right? That's what it indicates. And then when that happens, what do you have? Switch is off. Yeah, there's no N channel. What does switch is off mean? Well, the source and the drain terminals are disconnected. So the one thing that is kind of very common here is you are actually connecting or disconnecting the source and the drain using the gate terminal, right? So gate terminal is actually not shown over here because that's what you are controlling. Do we need to worry about not using it in the linear region and all that? No, no, no. So we are using it in the extreme regions, right? Cutoff and saturation. Like we are not even using it in the active region for amplification purposes. Either open or closed. Cutoff or saturation. All right, so VGS is less than VT. This is 0, switch is off, meaning source and the drain disconnected. Current can't go through. The other one is G is 1, which means VGS is greater than or equal to VT. I, indicating a 1, switch is on, which means connected. Right, so the gate actually doesn't show up in this one because that's what it controls, right? So it's like you are standing at the door, you only allow people to go in and out of the room. You are actually not part of that process. You are just controlling whether people can go in and out of the room or not. The story kind of flips for the pMOS. Like I said, the channel is P channel now. This is the P channel, positive channel, MOS. The symbol has a bubble on the gate. There's a bubble over there as well. The substrate is connected to VDD. The source terminal is also connected to VDD. And things are flipped. Gate is 0, switch is on. Gate is 1, switch is off. So what does the first one mean? The first one means VGS is less than VT. The switch is actually on, right? Switch is on means the source and drain are connected. Exactly the opposite. And then the other case is VGS is greater than or equal to VT here, switch is off. Source and drain are disconnected. nMOS is your typical MOSFET transistor. pMOS is its complement. nMOS and pMOS combined, you get complementary MOS or CMOS. So CMOS transistors are a combination of nMOS and pMOS transistors. There are two types of them, right? CMOS is two types. So that's your CMOS transistor. Let me erase all of this here. Let's talk. So what we have here is an nMOS transistor, a pMOS transistor, and you can see its symbol, right? That's your, let's identify the three terminals. We have this guy should be the gate, that guy is our drain, this guy is our source connected to ground. And because this is nMOS, the source as well as the substrate is connected to ground. And we are not showing the substrate, we are just showing the source connected to ground. For the pMOS transistor, the switch, the thing is flipped, but the terminals, we still need three terminals. You should have your gate, you should have your drain, sorry, that is your source. Source connected to VDD, drain connected to, the drains are connected together. CMOS, sure. Right, so those are your three terminals of pMOS transistor, three terminals of the nMOS transistor. Because it's nMOS, in order for it to function, source and substrate connected to ground. And for pMOS transistor to work, you need the source or substrate connected, source and substrate connected to a high voltage VDD. Now what we are doing here is we are trying to build a complementary MOS inverter, and right away you see that it is complementary because it has a presence of pMOS and nMOS transistors. Right? Complementary. Now what we have done here is we are saying that, okay, we are going towards an inverter. We are trying to build a NOT gate over here using CMOS transistors using one NMOS and one pMOS. We also have this capacitive load indicated in the diagram, and this is nothing but the parasitic capacitance that is a property of that MOS. You say, earlier I said there is an oxide layer between the metal and the substrate. That layer of oxide actually forms a parasitic capacitance, and there could also be some parasitic capacitance coming from, say, wires in your circuit. All of that is being described using this capacitive load. So that actually, limits how fast this inverter can be used, because that controls the propagation delay through the circuit. We are not going to be focusing on the usage of that. We are not going to be dealing with propagation delay right now. We are focused on whether this guy can work as an inverter or not. What do we have? We have connected the source VDD, source ground. We have connected the drain terminals together, and actually the connection between the two drain terminals is where we are measuring our output voltage, V out. And our input voltage is actually going to the same voltage, the same input voltage is controlling both the gates, the gate of the nMOS and the gate of the pMOS. Now let's try to see if we can get a NOT operation out of these. To do this, I will try to call these transistors by some names. What I'll do is I'll call this nMOS transistor using Q1, and I will call my pMOS transistor Q2. And then I will try to lay out a table on this side that will help me keep track of the state of these transistors as I change my input voltage. I'll have a column for input, I will have a column for Q1, I'll have a column for Q2, and then I'll have a column for V out. So I'm going to start all the way here, V in, then I will have Q1 here, then I'll have Q2 here, then I'll have V out over there. So I'm not looking at all the possibilities of my input voltage. I'm simply looking at the logic 0 and logic 1 state, right? So the input voltage can either be a low voltage or it can be a high voltage, right? So it can either be low or it can be high. So when it is low, can you guys tell me whether Q1 is going to be on or off? You see, this guy controls the gate terminal there. And I'm saying that it is low right now. So when this is low, off is right. Yeah. So when this is low, the N channel is not formed, which means the connection is not made, which means Q1 is off. So you can think of it like this, right? You can say, all right, this guy comes in from here and then disconnects and then goes there, right? VGS is less than VT. Yes, you got it. It's disconnected. So it's off. And I don't even have to worry about finding Q2 because it has to be complementary, right? So if this guy is off, it has to be on. And, I don't need to believe that. I can actually figure that out because V in is low. That is going, the bubble we know signifies inversion, becomes high, and then you have that the pMOS operation. So now this guy's source is going to be connected to the drain. The P channel is formed. It is on. Now, if this guy is off and this guy is on, let us try to see what happens to V out. So let's see. I'm going to indicate the off and on this way. Let's say I have this guy disconnected from this. However, this guy was connected with this. So what is V out going to be? Should it be 0 or should it be VDD? It will be VDD minus VDS, sure. So VDS we are going to ignore. I'm ignoring the on resistance of the transistor. But so if I ignore VDS, then it is going to be VDD, right? High. And in the next case, everything flips. I'm going to erase this guy, this guy, and then say, all right, now Vin is high, and if Vin is high, I'm going to get Q1 to be on. This guy is going to be connected here with this. And of course, this is complementary, so this guy is not going to be connected to this. This is going to be off here. And now what is going to be V out? Is V out going to be VDD or is V out going to be grounded? Grounded, yes. So low. You guys see that? And let's tie everything back to the inverter. Low goes in, high comes out. High goes in, low comes out. When I'm talking about low comes out, I'm talking about the voltages, range of voltages that is going in and out, right? So this low and high, if you associated low and high with binary 0 and 1, you get a truth table for this guy. Input 0, output 1, output input 1, output 0. That is your inverter. Symbol, triangle, followed by a bubble. Here, this is your input, here is your output. And we are using V in and V out to indicate the voltage at the input and the voltage at the output. Okay, so after this discussion, I'll ask you guys this. How many CMOS transistors did I need to make a NOT gate, CMOS NOT gate? How many transistors did I need? Two. So I need two CMOS transistors to make a I need two transistors to make a CMOS NOT gate. CMOS inverter, I need two of them. Which transistor in this case is responsible for the output becoming high? Which transistor is responsible for the output to become high? The pMOS transistor. Absolutely right. So what I'm going to do is any one transistor or any bunch of transistors that are making the output go to high possible, I'm going to call that my pull-up network. In this case, I only have one transistor in my pull-up network. What is that? It is a part of your circuit that is responsible for pulling the output up, pulling the output voltage to high, called the pull-up network. In this case, I only have one pMOS transistor in my pull-up network, but there is a possibility that I will have many transistors. It will depend on the logic function. It will depend on the input, number of inputs to that logic function. Next, what should I call this guy? If that is my pull-up network, this is my pull-down network, because that network of transistors is responsible for pulling this voltage down to 0. So every CMOS circuit that you will see will have a pull-up network and will have a pull-down network. And the good thing about this is the convenient thing about this is the complementary nature, which means if your pull-down network has transistors in series, then your pull-up network will have transistors in parallel. If your pull-down network has transistors in parallel, then your pull-up network will have transistors in series. always going to be complementary. Your pull down network will be a bunch of nMOS transistors, and your pull up network will be a bunch of pMOS transistors. Right? So it's going to become very, very convenient as we go on. Does the inverter triangle on the side also have VDD and VDS connections? For the symbol, we don't need to draw. Right. For the symbol, we don't need to draw. We can just plug in the input and the output. So you can kind of put them here, but we are not going to draw a detailed schematic. For our logic symbol for NOT, we can just use this. All right. Come on. Here. Now this is the switch model for the CMOS transistor, a CMOS inverter. The idea is, if I were to replace the nMOS and the pMOS transistors with switch models, then I could also analyze that CMOS circuit, right? So we are trying to make simpler by using this switch model instead of CMOS transistors. So when the input is low, the nMOS transistor is open, the pMOS transistor is closed, so your output is high. When the input is high, your nMOS transistor is closed and your pMOS transistor is open, so your output is low. You have seen this already with transistors, but now you're looking at things that are becoming easier, right? So this is your Q1 and Q2 from before. This is your Q1 from before, your nMOS. And this is your Q2 from before, pMOS. And of course, the same input voltage is controlling the gate terminals of both the transistors. So I hope, after our detailed discussion on the CMOS circuit itself, I don't need to spend too much time on the switch model. All right, questions so far? Let me take a minute here to see if you have any questions. All right, so let's try to talk about a buffer now. What am I doing? Add page later, after. So an inverter needs two CMOS transistors. How about a buffer? Any guesses? What do I need for a buffer? One? No, I can't do it with one. I need two at the minimum, right? Because I need one to be complement of the other. No, I cannot even do that. I cannot swap the pMOS and the nMOS, because in order for the nMOS to work, my source and the substrate need to be grounded for nMOS. And the source and the substrate need to be connected to high for the pMOS. So I can't even switch them without affecting the logic. Two inverters connected. Brilliant. Yes, absolutely. So the way you make the buffer, it's very interesting. So let me actually talk about why we need this, right? Like motivation for this. Why do we actually need a buffer? So, seems wasteful. All right. So here, so Andrew, let me clarify this for you. All right. Suppose you have, because buffer is not doing anything, right? Like it seems wasteful, right? That's kind of not potentially circuit. All right. So I think this is going to be very interesting, you guys. The motivation for designing a buffer is interesting. So let's get into it. Suppose you have something over here and you're connecting that to something over here, right? Like these are some section 1 of your circuit connected to some other section 2 of your circuit, right? And you're connecting them using a wire, right? So what is that? That's the output of section 1, which is connected to input of section 2, right? So suppose what happens is, if this guy is, say, a weak 0, right? A weak 0, say it is the output of section 1, or maybe section 1 gave out a strong 0, but because of the wire or because of more things being connected at the output of section 1, it somehow became a weak 0, right? And it goes into section 2. Maybe section 2 registers it as a 0, or maybe it gets confused and maybe looks at it as undefined. I don't know, right? But I would have really loved to put something in the middle here so that that weak 0 can actually be converted into a strong 0, like a repeater exercise. Absolutely, right? So if I put a buffer right in the middle, that actually converts a weak 0 into a strong 0 or strong low, so that now section 2 is going to register that as, oh yeah, you're telling me this is logic 0. So the reason why we have a buffer is to solidify a voltage level, a logic level. So a weak 0 can be translated into a strong 0, and similarly a weak 1 can be translated into a strong 1, right? So if you're putting a bunch of things together, because of the numbers increasing, you may have trouble maintaining those voltage ranges, which is why you need buffers. You guys see that? A simple wire to connect the two will not cut it, right? You can end up into a lot of problems there, which is why we need a buffer. Now, how do you make one? Well, a buffer whose symbol is just a triangle is equivalent to one NOT gate followed by another NOT gate. That's it. One NOT gate after the other. So if a 0 goes in, a 1 comes out here and a 0 goes there, right? So it doesn't change the logic. However, when it's doing this 0 to 1, it is regenerating that bit. When it finally becomes a 0, it is going to end up being a strong 0, at least stronger than this one. And the same works for the other case. If 1 goes in, 0 comes here, 1 comes here, right? So what you really care about is the input and the output are not changing. However, we are solidifying that voltage level. That's the attractive feature of that buffer. We are going to be using buffers many times. So I hope that you get some good understanding from this discussion. Why do we actually need the buffer? All right. So how do I make one? How do I, can I sketch the CMOS transistor level circuit for a buffer? Well, I have one here. I just need to put another one in front of it, right? So I'm done. So what I'll do is I'll quickly do this. Try to do as quick as possible. And boom. This is going to +5. And then this is my input here, right? So this is my first NOT gate. And then I will simply copy paste this. Oh, come on. And I'm done. This is my input. This is my output. So the output of one went into the input of the other. Again, you have 4 transistors in this case: Q1, Q2, Q3, Q4. Q1 and Q3 are part of the pull down network, right? These two guys are part of the pull down network here. And Q2 and Q4 are part of the pull up network there. And I don't even need to draw 2 plus 5s. These are both connected to each other, 2 plus 5, and these two are grounds anyway. I don't need to draw 2 grounds separately there. But the idea is the output of one gate is going to go into the input of the next one. Questions about this? How do you get a buffer? So how many transistors are required to synthesize a buffer, to implement a buffer? 4. Brilliant. 4. I need 4. So 2 fixed for inverter, 4 fixed for buffer. You guys see that? All right. Now we have 10 more minutes. So let's see how much we can talk about things. All right. We talked about this. All right. Let's see here. Bunch of things I'm going to erase and then talk about this. Now let's try to make CMOS NAND gate. And there's, as much as I want to, I can't do it right now. Let's try to talk about that sometime later. I will follow up on Minecraft and redstone circuits with you guys. CMOS NAND gates. We said earlier that for AND and NAND, I need switches in series, right? Signal repeater block with redstone dot signal. All right, so Josh has you covered. All right, so here we have 10 more minutes, you guys. Let's get into NAND gates. Now this is the things. This is the place where things get easier. So let's take a look here. You have for NAND gates. What we said earlier was need switches in series for NAND as well as AND. Now, if I put two nMOS transistors in series, like so, right, one after the other, then this is my pull down network, right? That's the network. So A and B are controlling the inputs, the gate voltages of Q1, Q3, Q2, Q4 actually. A is the gate for Q1 and Q2. B is the gate for Q3 and Q4. Q1 and Q3 are in series, nMOS. Q2 and Q4 are in parallel, pMOS. Q2, Q4 combined, I get my pull up network, because without that Z would never go to high. And Q1 and Q3 are my pull down network. All right, so I'm going to identify this as my pull up network, which right now has two pMOS transistors in parallel. And I have, oh, come on, snap. This is my pull down network with two nMOS transistors in series. And all of this is being done to get to this particular logic symbol, right? This is your NAND, and followed by the bubble, which indicates inversion. That's your NAND. In other words, this symbol logically can also be written up as AND followed by NOT. How would you come up with this circuit though? Oh, so here, this is how I would think about it. AND and NAND, right? AND and NAND, they both need switches in series. That's first. Second, switches, the typical switch is what? When I switch it off, things should turn off. When I switch it on, things should turn on. Which type of CMOS transistor represents that? It is the nMOS, right? Not enough voltage, off. Enough voltage, turn on, right? So I would associate the normal behavior of a switch with the nMOS transistor, whereas the pMOS transistor is going to be exactly the opposite. So switches in series. All right, so let's put two NMOS transistors in series. Right away, I got my pull down network and my pull up network will be complementary. Right, so for this particular case, I tried to make the connection between NAND to the configuration of the switches to the NMOS transistors, pull down network, pull up network has to be complementary. That's how I got the two pMOS transistors in parallel for the pull up. You see that? So it's and you can do it the other way as well. Let's talk about NOR, right? So if you're talking about NOR, you would say, all right, for NOR, I need two NMOS transistors in parallel. That's my pull down network, which means that my pull up network will be two pMOS transistors in parallel, in series. You see that? So if you figure out one, you can figure out the other because of that complementary nature. And we don't need to just look at statements, memorize statements. We can just look at the analysis, right? So if we have A, B being connected to the gates of Q1, Q2, Q3, Q4, I can start looking at a table like this, which is monitoring all the four possibilities between A and B. Because A and B are two binary variables in this case, they can both be low or low, high, low, high, right? And then for each of these combinations, I can monitor the state of the four transistors, on or off. Now, then I can say, in order for Z to be connected to ground, both Q1 and Q3 has to be 0. Both Q1 and Q3 has to be on. Right? So only when Q1 and Q3 are on, Z can go to 0. That only happens for the last possibility. For every other possibility, one of them is going to be off, open, and that is not going to allow Z to go to ground. And in fact, you will have one or the other path between Q2 and Q4 that connects Z to high. So if you keep monitoring that Q1, Q2, Q3, Q4 state, eventually you will see that your output Z will be high, 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 low, right? So this is like 1, 1, 1, 0, which is exactly the opposite of the AND function, which is 0, 0, 0, 1, right? So for AND, we had 0, 0, 0, 1, which was both need to be high for it to be high. For NAND, it is exactly the opposite. Both need to be high in order for it to be low. So we got the NAND function by this. So how many transistors do you need to get that? How many transistors did we use here? We used 4 transistors. Absolutely. So we got 4 transistors, 2 of them nMOS, 2 of them pMOS. What if I extended this to a 3-input NAND gate? How many transistors do you think I need for a 3-input NAND gate? 6 would be exactly right. I would have one more transistor in series here. I would have one more transistor in parallel over there. Beautiful. Now let's talk about something that is kind of, we are going to try to connect few points here. Let's see, after, sure. So how do I get AND then? How do I get this? Not NAND. Yes, brilliant. Yes. So this is, you first design a 2-input NAND, then you cascade a NOT gate in front of it so that, these two things cancel out. The two bubbles cancel out. Double negation cancels out, right? So when you have a bubble and you have another bubble, the bubbles cancel out. 0 becomes a 1, 1 becomes a 0. Double bubble. Yes. Another prediction to make AND equal to NAND. So what does that mean in terms of our circuit diagram? Well, let me see. I need this guy, right? I need all of this to get my 2-input NAND gate, and on top of that, I need to put an inverter in the front. Based on that, can you guys tell me how many transistors are required to make this guy? A 2-input NAND gate. 2-input AND requires how many total CMOS transistors? 6. Right? So this guy requires 4, this guy requires 2, and then you get the 6. You guys got it. Now, based on this, you guys can, answer a variety of questions, but we will expand on these ideas when we come back on Tuesday. I'm going to stop recording here in just a second.